Hello, everyone. Thank you for joining us today for this webinar titled Advanced Optical Composite Validation and Digital Manufacturing. It is brought to you by Composites World and presented by Trilion Quality Systems. My name is Ginger Gardner, and I'm a senior editor at Composites World. The continuous advancement in composites is leading to better, cheaper, and higher quality parts. The development of full-field optical measurement systems is improving how we test and validate these parts. Companies in aerospace, civil engineering, sports, biomedical, and automotive are turning to 3D optical testing to ensure part quality and long-term performance. In this webinar, you will learn how 3D digital image correlation and dynamic photogrammetry is used for 3D shape displacement, strain, and vibration measurements, as well as for validating FEA models. You will see real applications in the composites world and discover not only how Trilion's ARAMIS 3D optical testing system delivers superior data, but how it also helps companies save time and money within their testing processes. Primary topics include using 3D optical testing for strain and deformation analysis, how to measure high-speed tests accurately, and understanding how optical measurements make manufacturing cheaper and more efficient. Our presenter today is John Tyson II, President of Trilion Quality Systems. This company is a manufacturer and developer of advanced optical measurement systems. As founder and president, John Tyson has more than 35 years of experience in the field of laser-based and optical inspection methods, including holography, shearography, digital image correlation, and photogrammetry. He has 8 patents in the field and has developed test applications for the B-2 stealth bomber and the space shuttle. Tyson is a graduate of Duke University with a BSc in mechanical engineering and material science. He is also a professional engineer. Before we begin, I would like to remind you to please submit your questions by typing them into the question pane on your control panel at the right of your screen. We will answer these during our Q&A session at the end of this presentation. And now I'm going to hand it over to John Tyson.
Thank you, Ginger. My name is John Tyson, and wanted to talk about how optical metrology is able to bring advanced capabilities to the composites manufacturing world, and a little bit about how the technology works. So the technologies that we're working with are a stereo imaging capability. So just like our eyes can see where something is in 3-dimensional space, we're able to use digital cameras to make these measurements very highly accurately and in a full field way, like humans see things. So our metrology toolbox starts out with ARAMIS, and this is our core tool for doing tracking deformations and strains in materials in a full field way. All our sensors are like mechanical sensors, but these are as accurate, if not more accurate, than your typical mechanical sensors of strain gauges, displacement sensors, accelerometers. And it works directly with your finite element model. Our Argus technology is now used in basically all the stamping in the United States and Canada for metal formability. And so basically all facilities of GM, Ford, Chrysler, Nissan, Toyota, Honda, you all use our equipment for studying the formability of sheet metal. Tri-top is another tool that we use for sort of like a portable CMM. We can make measurements over large structures, and it also provides automated stitching for our other measurements. So we can allow us to, in this case, look at a railroad car and map all our measurements from any one of our other machines into the same coordinate system, and all in CAD coordinates. We also have a full range of CT equipment from the GOM CT through a complete set of Zeiss CTs that we use for additive manufacturing, as well as broad range of materials where we can look into the structures and see dimensionally how the structure was made. And then our ATOS systems allow us to do structured light measurement of structures. So this is basically white light scanning. We now call it blue light scanning, but a single frequency, but where allows us to make precision measurements on parts. And so all of these technologies are high precision measurement tools for industry, and you're able to make measurements over the entire structure or throughout the structure in really strong ways. We also have a number of other kinds of technologies. Our high-speed camera technology allows us to take these same tools into high-speed realms, all the way up to millions of frames per second, depending on the application. Vehicle drop tower crash world to high-speed material measurements, ballistic and blast type stuff. Our ARAMIS thermography is also very wide-ranging and capable. Developed originally for the B-2 bomber program. This allows us to do in situ measurement of materials and structures during manufacturing, non-destructive testing, as well as structural health monitoring. And we offer all of this as engineering services, as gaining the experience of how to use these and be able to help our customers in a really strong way to implement them in the best way possible. So getting into the ARAMIS technology, this is a full field optical strain measurement capability that allows us to be able to measure what mechanical sensors can normally measure. But when you have a finite element model, it becomes crucial that you understand holistically what's going on. And that's where our tools come into play, where we're totally able to integrate with finite element model, with CAD, and be able to understand dimensionally and locally with strain on how the materials are performing. And these, again, are all measuring 3D coordinates, deformations, and strains. It doesn't really matter what the material is. So we can look at complex material sets to understand how they're working. In real structures, in real testing, we're considered an A-class extensometer. Most of your extensometers in material testing are Class B extensometers. Where we're measurable, we are considered a Class A extensometer. So we're as accurate as any of your other mechanical sensors and can be much more accurate depending on how you configure the system. So we're using a stereo-based imaging system to be able to look at the structure, and we can use target dots to measure displacements very easily. And so a normal test like this might take days or weeks to set up. We can have this test set up in a few minutes. The speed of what we're doing is really incredible. Also, in this case, the object is moving throughout the field of view. We've used the knee itself as a coordinate reference. So it doesn't matter, our cameras could be sitting on bungee cords and we still get micron level displacement measurements relative to the knee in this case. We can also put a pattern down, and the pattern allows the software to create its own targets with it throughout the pattern. And so we get a continuous realm of node points across the surface. In this specific case, the finite element model or strain gauge might be able to get an understanding of what's happening in the gross considerations here. But we're able to see even the Lüders bands that are occurring, which is a crystalline level structural effect in this steel. So we're using a stereo imaging tool. We can bring in the CAD, so we're in true CAD coordinates, and we're imaging holistically the entire part of the specimen in a very quantitative way. And so we're non-contact, so our measurement testing is just minutes of setup to make measurements that traditionally take days or weeks to prepare. We're full field, so instead of being able to see the defects that or the areas of concern that you know about, we're able to see holistically what's going on. And so you really understand how your whole structure is performing in a really solid way. One good user at General Atomics said, if you're not using digital image correlation for your measurements, you really don't know what's going on in your composite parts. So it's an engineer's toolbox. We're measuring true 3D shape, deformations, strains, accelerations, all this kind of thing. From very small fields of view, it's all optical. So it doesn't matter what lenses and that kind of thing we have on there. But we can go from very small fields of view to very large fields of view in order to understand the dynamics of materials or systems. Again, because we're measuring displacements and shape, we're really completely material independent. If you have metals working with elastomers and composites and complex configurations and metallic inserts, we're measuring how all of these components work relative to each other, which becomes really powerful for finite element modeling, because most of these interfaces are just assumptions that you have to make. And we're also quite tremendous range of operational range, from deformations and strains through dynamic to very dynamic situations, all the way up to millions of frames per second. Looking at fracture in glass as it's occurring is quite powerful. Also, since we're full field, when we're doing vibrational analysis, we're really holistically understanding the operational deflection shape of the component. Unlike laser scanning vibrometer or accelerometers or something, you're looking at a couple points across the field of view, or they're not temporally synchronous. All our data is temporally synchronous, so it's you're getting the true operational deflection shapes without assumptions. And so all these capabilities lead to a very powerful set of tools to allow us to do finite element model iteration as well as validation, and component and structural response validations. So the possibilities are quite endless where we apply this, from materials measurements into structures into real manufacturing applications. And as you can see, some of the industries we work in and the kinds of applications that are used. So getting into material testing is really the beginning concept of, what are your materials doing? And this is, of course, crucial to everything from designing a product to its final operation and its long-term success. With material testing, we're able to holistically understand what's going on and quantitatively measure very precisely the complexity of modern materials, and especially when you're getting into composites. The understanding the true material properties and failure modes, this kind of things, are quite crucial. So typical examples are, the precision measurements of not only local considerations, but global considerations. And so, clip gauges or strain gauge might give you some global response, but ARAMIS is able to track in that necking and fracture area considerations. Also getting into flow fronts and local material characteristics. So what concerns you have typically are with making measurements, like in this clip gauge here, you can see it's not measuring what you think it's measuring, and mainly because of maybe clamping forces weren't actually equal, or the clamps weren't parallel, your fixturing problems, that kind of thing. So it ends up being a really powerful tool. NASA proved that ARAMIS materials measurements are more consistent in making material property measurements than traditional methods. And they use our technology continuously for doing this. So the idea of being able to precisely measure your materials and get consistent material property is crucial to everything we're doing in the industry. Typical example here, in a 4-point bend test, we see actually just using a mirror, our system doesn't care, and you see both the tensile and compression sides of this specimen in a very simple way. And again, just a very simple setup. You get into shear testing, and this becomes just a really powerful feature of the technology, because shear is, typically how one plate is moving relative to the other, and you're going to make assumptions about the shear. But here we get hundreds of measurement points in through the shear region to truly understand how shear works. Actually, this is how I originally got into digital image correlation, working at NIAR. We had some shear panels like we see over on the left there, and trying to do that with holography 20 years ago was difficult, a little too difficult, and digital image correlation turned out to be the perfect tool for doing this. So it's really taking the capabilities of what holography could do in the scientific lab and taking it out to be a real mechanical engineering tool. Then you get into things like fracture, and fracture, of course, is very complex, and understanding how it's going. One of the powerful tools is that not only are we measuring like mode 1 characteristics like a clip gauge could measure, but we can measure mode 2 and mode 3 just as easily along the entire length of the crack. And so in any application, even in the field. Another good example is instead of having a notch specimen, you can just run a fracture test and watch how your cracks are propagating. And then after the fact, put down your displacement sensors and now measure the displacement sensors of the cracks that will develop. You're seeing the data after it's happened, and now you're able to measure precisely what's happening to the component. Once you know where the final result, you can put your gauges down after the fact. One example of this was working with the B2 program. We developed the ability to do digital image correlation, thermography. And so ARAMIS thermography allowed us to look at the aft deck of the B2 bomber with the hot gases flowing across the surface of the deck and look at the fracture in these components. This helped them solve a problem that had been nagging the Air Force for 20 years. We've now applied this to being able to look at materials in an oven, as an example, looking through windows, to here's an ARAMIS thermography measurement where the strain is on one side, and this is what's happening or going to happen, where the temperature is showing you where the stress is actually happening. And so you can see the temperature flow and the strain together really tell the whole story of what's going on with this material and structure. This is quite powerful when we get into additive manufacturing applications, where either in testing additive manufactured parts or in the assembly of them, we use ARAMIS for doing metallic assembly. So the thermography is able to look at the weld bead while we're building, and the ARAMIS looks at the development of strain and the strain effects in the material as we're building them. You can see that understanding things holistically really gives you tremendous information about how to look at additive manufacturing applications. So we're considered a NASA spin-out technology. We were used early on in the return to flight of the space shuttle, looking at the ballistic impact of foam hitting the carbon-carbon leading edge. And then this is the real leading edge of the space shuttle, where we're looking at this data was used to validate the LS Dyna models to get the shuttle flying again in 2004, 2005. We then did some critical work on the Space Shuttle external fuel tank during the Discovery's last launch. We did some, this is a 6-hour test showing how the external fuel tank was failing and the repairs that they had, and we were able to launch the last 3 flights because of the work we did there. And then at NASA Langley, substantial amount of impact testing of not only vehicles, but spacecraft, that kind of thing. And you can see here's the Orion spacecraft dropping into tank and our coded markers, hot-fired rocket motors, and the HIAD 25-foot diameter component in high-speed wind tunnel, looking at the re-entry conditions during landing on Mars. And this is the ballistic impact of the leading edge of the space shuttle wing, and you can see our impact area, and this is the data that was used to validate the models. Notice the strain gauge that was in the field of view completely missed the impact itself, and the full field really answered the questions. We also use this for blade out tests and jet engines, the primary applications in blade out tests now, as well as looking at long-term operation of vehicles. We've done thousands and thousands of hours of testing of jet engines, and we're looking at the dimensional properties of it during the testing, or in this case, a impact test into a blade. So here's a ballistic impact into a blade, measuring the full field response of the blade. Our work on helmets brought back hundreds of thousands of helmets out of Afghanistan that were defective. We helped help that happen. Here's the missile firing, looking at the roll, pitch, and yaw during deployment. We were also used on the structural testing of the Boeing 787. There was 10,000 foil strain gauges on this vehicle, but our 4 ARAMIS systems in and around the wing root added another 200,000 strain gauges. And this was crucial for the FAA certification. But in the next generation testing, we're going to be reducing the costs of testing by 50% by reducing the labor requirements and faster installs and saving heavily on schedule. But also providing better data and synchronous data throughout the whole testing structure. This is some of the testing that was going on with the loading. But anyway, the wing root area was crucial to the measurement. So model validation has been crucial to the implementation of the technology. And in simple material structures, the model and our ARAMIS result, which the Boeing FEA guys say is seeing the reality of what's really going on. In simple homogeneous materials, you're seeing good equal response in the ARAMIS result versus the finite element model. The local variations here are true local variations in the material. So this is, you're seeing right down into the material structure. But when you get into real components, the model versus the reality is sometimes very much different than anticipated. And you can see in this case, a strain gauge expecting to see a high strain concentration right there, where it was not seeing anything caused by structural defects in the material. So Boeing has shown that a VP had said, find a better way because strain gauges were costing too much. That ARAMIS was 10 times cheaper to use than regular foil strain gauges. It was 50 times improvement in manpower. So much simpler to install and implement, and 100 times more data. So we use this on the FAA certification of the 787, and it's been used on the 777X and various other program plans going forward. So let's give you a little demonstration of the technology, and this is a typical stereo system. This is adjustable base, so it's simple to set up and be able to be very flexible for lots of different applications. And you can see that the cameras can be adjusted right and left. We have some lighting that's nicely adjustable. And so we can then aim and point this to the desired area of application. And so typically either on tripods or camera stands, it's easily adjustable. Now here's a typical example of a part. This is a composite sample that we're just going to structurally load, so we can just take a look at it. And this is how the software is working. You're seeing the views from the right and left cameras, and we've patterned the surface to create the pattern that we'll be measuring. simply setting up the system and choosing the choice of triggers you want to do, the speed of the measurement, all from a simple toolbar. You just follow the steps across this toolbar to run the system. So now it's ready to start measurement. The original calibration to calibrate the two sensors probably took 10 minutes. So it gives you a sense of setup time. And so Joe is sitting there bending the part a little bit and comparing the part. So we finished the test, and this is just a manually loaded composite part. So you can see the bending that he had done to the system originally. And you can just use the bottom toolbar as a time bar and just adjust the time as desired. Now we can create a surface component, and the surface component allows us to just create a surface from the dot pattern that we're tracking, and it's now calculating that. So here it created that, and it's broken the whole image up into these little windows called facets. And this facet is how we get a 3D coordinate point. And then you can see one a little bit to the right and a little bit to the left. So that's the next one over and down. So there's probably 10,000 measurement points across this surface. So you can see at the center of each one of those nodes is one of our measurement points. And it would be a rosette strain gauge at any of those points, or a 3D coordinate point, whatever measurement you want to make. And over time, you were looking at velocities and accelerations. So he can just mark off an area if he wants to establish a measurement region, so the software can doesn't have to look beyond the area we're interested in. And he set it up so that we can look at the reference length. So you can see here the gauge length across the field of view is something in the realm of between 3 and 4 millimeter gauge length for our strain measurement. So now you can see the surface component is tracking well on the motion. And he can now go in and create whatever parameters he wants to look at. In this case, we're seeing the reference coordinate system from the cameras, but we can bring in the CAD and now get into the true CAD coordinates. So we know all our measurements are consistent with the CAD. And you can see this structure has internal ribs and various other things that are of interest. And so he's going to do a alignment of the CAD and the component by just clicking on a point that might be close to similar on the two components. And then he can do a best fit to that surface component to see how it aligns. Boom. Now the two are aligned. And you can do further alignments as necessary, but basically you're now in the true coordinates of the speed of the part, and you're within a quarter of a millimeter of alignment across the whole field of view. So it gives you a sense of, the accuracy of that alignment. And so now the coordinate system is in the CAD coordinate system of your design, and we can choose now what components we want to do. What do we want to look at? Displacements, strains, velocities, accelerations, just hundreds of choices, but we can define the choices to which we specifically want to do. In this case, looking at major strain in the system. Now calculating that strain, that principal strains across 10,000 measurement points. And so now you can see the strains during the test. It gives you a good sense of your strains going up to 9,000, 10,000 microstrain. And then we can use this to validate. We can bring in the finite element model and do a direct comparison to understand exactly how this matches to your modeling. And as you can see, you can put your sensors down after the fact. So in this place, he's putting down the specific sensors. Here are the throughout the test, the strain from the 4 sensors he put down. And it's as simple as that. It didn't take hours of time to put sensors down and make measurements. And not only that, you can put the sensors down right where you need the data, not where you estimate the data will occur. And then you can generate a report on this really simply. And you can see the internal structural response on the surface there. And that's those strain fields were caused by the ribs inside. You can see those ribs. And so the strain fields are what's, you can see the strain fields are directly associated with those ribs there. Again, generating reports is just a piece of cake. Just click of a button, and you can generate the reports that you need as you need to. And you can do this all for the first part. And after that, this can be a template for every other measurement you make. So all follow-on tests you do are all reported exactly the same way. And so they're all got the same scaling, the same configurations, and it's easy to understand how one result compares to another. And he's turning that into a video. And you can store the report as a PDF, and with modern PDF, it stores the videos also. So now you can have a complete video stored in your report. And again, you can see it's just taken minutes to do the entire test and the entire reporting all at once. So the speed is quite powerful in achieving all of this. So let's get into digital manufacturing now. So we've seen how this technology can be used for studying materials and really holistically understanding how a material and structure can respond. Now let's look at digital manufacturing and how these optical tools can hugely benefit us in the manufacturing world. So we can use this for in situ monitoring, understanding the quality in real time and being reported across your company structure all in real time. So everybody's in sync with how everything's going. We can be doing digital assembly and monitoring the digital twins. So in digital assembly, we can be doing this with toollessly. So instead of having a strong hard tooling that are very expensive, 40% of the cost of an aerospace program is the tooling itself. So if we can get rid of some of the tooling and utilize digital assembly tracking, then we can be and precision guided assembly can be very powerful. Then we talked a little bit about structural testing and reducing the costs there and providing you much better data. And another really advanced area is structural health monitoring, using this full field optical tools to understand the health of your entire vehicle. So we'll talk about that. So digital manufacturing and the digital twin, here we're able to monitor the assembly of components very simply and accurately. And it's based on our ability to just measure parts. In this specific case, This operator is measuring a component with a touch probe, we call it, and we're able to just 3D track the point he's touching to by seeing the target dots on the component that he's using. And this is very dynamic and very flexible, and typically rapidly improving the measurements being made. They're being made directly to CAD coordinates, and very much faster, typically 10 times faster than traditional methods. Now in this specific case, he's assembling a dashboard, and he's tracking these two holes in the back of a component that he wants to make sure they match to the CAD inside the structure. So here he's assembling the component, and he's you can see that the assembly is getting close to being precise. And this is the two mounting holes inside matching to a component inside, and just seeing the outside of the component to be able to see how these are all matching, and checking not only against CAD, but being able to check against other products that you've made also. So let's talk a little bit about in situ monitoring. In situ monitoring, we can work with the laser alignment tools to provide hand layup guidance, and then thermography capabilities to look for FOD detection and document quality assurance of the entire assembly in your composite layup, and the digital twin documentation of that. And you can see here some a foreign material. This was a glove tip, and some bridging happening in this structure. To be able to see the EOP, again, what is the tolerance for each application, and automatic real-time feedback on each of these parameters, so that you can make sure that your part is being made right, and before it goes into the autoclave. We can also apply this to working in ATL and AFP applications of tracking the components and how the alignments are really working, looking for voids, FOD, and that kind of thing. And you can see here our thermography equipment on a robotic layup, and tracking the fiber as it's coming out of the robotic head. And in the end, we end up with a three-dimensional shape of your component, in this case a flat panel, and we're able to see a twist in the fibers up here, and so a defect that is showing up in the final build. This is layer upon layer, the quality feedback. You can see in this case some various defects that were put into the structure, and then the system detecting these defects as it went through. And the ability to then, once it's in the digital twin, be able to then document every defect that's come through, what the acceptable below tolerance or above tolerance or close to tolerance parameters that you're seeing there, and how those document. We can also be tracking measurements but from the quality inspector. And the quality inspector measurements that we are doing for the layup applications have literally been 10 times faster than the traditional methods, and completely documented automatically of how the alignments are all made, and each measurement as required. So the idea of being able to do, provide the laser guidance, fiber alignment, FOD detection, then you're making a perfect part, so you can autoclave a good part. We can then 3D scan this part, get the true dimensions versus CAD, and then be able to do adhesive bonding, digital assembly, and QA checks all automatically, either with hand layup or robotic layup, in very good ways. All a similar process, and all being tracked in the digital twin. So in digital assembly, we're going to be doing, again, using our system to track components. We're able to give precision operator guidance, and it generally is in the realm of 60% faster than traditional methods, and you're based on the true 3D coordinates of the component that you're doing, so you're much more accurate. And also the idea that we can bring back knowledge from the manufacturing floor back into engineering in a really good way. And this sense, you're tracking the assembly of various components and seeing how they match to the assembly requirements. And after curing, you check to make sure that the parts are built to assembled tolerance requirements. We can also track things like click bonds and other components going in space or alignments. And we just put a tracking tool on and track it right into position. Or in this case, we have a drill guide tracking tool, and we can move this into position very accurately. And on the 6 degrees of freedom motion of a true 3D component. In the real operational use, they found that the measurements we've been making on real structures, just using your standard operators, so much more accurate on true 3D structures and way faster, so typically 10 times faster. We can also measuring manufacturing strains, which then become the baseline for long-term structural health monitoring, which we'll talk about. So not only can we track people moving click bonds into position or drilling operations, we can track robots very accurately too. And this becomes much higher precision than traditional robots. And you can also use lighter, simpler, even mobile robots to do the work of large and embedded robots from previously. You can see here tracking the robot in throughout its motions in 6 degrees of freedom. Not only X, Y, and Z, but roll, pitch, and yaw. And here's a little example of our use of tracking a robot. We have the CAD of the robot in the component, and here we're tracking 6 degrees of freedom, how this robot's moving. From whichever perspective you're interested in studying it. And more importantly, we know where that head is relative to the tool. In this case, you can also put it from the head's perspective or from the floor's perspective. And here you can see the motion of every component as tens of thousands of points all simultaneously. So again, tracking click bonds into position, doing digital alignment, automated drilling operations, even blind hole drilling. I'll give you an example of that in a moment. And just doing general assembly. Again, getting away from tooling if there's a way of reducing the costs could be, especially for custom articles and things like that, becomes very powerful. So let's give you a little demonstration of this. This is Joe again giving a demonstration of the capability of an alignment using our RVAT, a real-time virtual assembly tooling. So we've brought the CAD in to where we want to do this assembly, and we can track the parts into position. And in this specific case, the multiple alignments need to be made, the composite assembly needs to be put on there, and we're going to put some click bonds on and do some drilling. And so you can track the instruction for each step, and the operator can send back recommendations on what needs to be done, how it could be done better effectively. And so many times our operators are as knowledgeable as anyone on how to build these components. And you can see the alignment of each of these components into place and making sure that they meet the requirements. And when putting the composite sample on, we're going to mount some click bonds. Typically a click bond, I know one customer took 1.5 days to mount 10 click bonds. We can mount your click bond within seconds with much higher accuracy. And so it's just going from one unit to the next, just with our little click bond tool, put on top that allows us to track it into place. Once the click bonds are in place, now we're going to do a sample drill. This is used extensively in composite manufacturing, and again, 10 times faster and hugely more accurate than traditional methods. So he's tracking it into position, and then he can drill it. Now this is a blind hole. This composite, a flat composite specimen, he's drilling into the hole below, and just not the kind of thing you can do traditionally. And be able to report all of this very simply as a digital thread. It's all captured. The quality of each operation is captured into the as a digital thread into the digital twin. And here you can see the complete reporting of the works that he did, and just as an automated report, if this is a repeatable operation, and to be able to directly compare this to your in your digital twin. So let's talk a little bit about the digital twin. You know, what are we trying to achieve with our, we call it our XI digital twin. There's a lot of digital twins out there. You got to differentiate yourself here. So our XI digital twin captures these RVAT digital threads during the manufacturing process and allows that each component, we have the CAD drawings, the scan of those components, the engineering data, assembly data, and QR data that have come through all these measurements. And each becomes a digital thread in the manufacturing system and is then documented as built in the digital twin. Then once you have the digital twin, you have the entire assembly of your vehicle, you can dive into a component. So it becomes a graphical digital interface to all your structures, your ERP, MRP, your engineering, and you can dive into a structure, look at all the engineering data around, you know, in this case, say a wing spar, looking at the materials, baseline data, the QA data, assembly data, NDT data, all captured into the digital thread. And this becomes, you know, a complete graphical interface into all the components in your vehicle, and just making it a simple way of understanding all this data. And you know, you're not dealing with the adhesive properties on some file and locked in someone's desk. Here, it's all accessible to everybody all the time. So the idea in the digital twin is that we can go into a component in this specific case and understand how it's assembled. The quality of this is immediately reported to quality engineering. Quality engineering can buy off on this component assembly and or fix it as need be in real time. So the parts are being made perfectly all the time. Let's get into some structural testing now. We were used on the James Webb Space Telescope by Northrop Grumman to understand the deformations and strains during structural testing of the bus structure, which is the core satellite structure down here. Each side is about 10 foot wide, and our 4 ARAMIS systems basically saved them a week a month for a couple months of testing, and saved them $2 million in the testing project. And that was 2014. That equipment paid for itself over and over again during the test, and is free from then on. So again, the idea of being able to make these measurements, if you assume that now the equipment is free, the testing is free and super fast to do. We did the similar structural test on the 787 wing and used this to validate the LS Dyna models for the FAA to show that there was no load pass that it didn't know about. For complex structures like landing gear, we do ARAMIS robotics. And so here we're doing the automation of the measurements during the testing. And you can be looking at hundreds of measurement areas with thousands of measurement points to really understand complex structural response. In this case, this is a large wing structure, a body structure actually between 2 wings of a vehicle. And we can see the CAD overlay and the true displacements that are happening across the field of view. This is about a 6-foot field of view during this loading of the component. And then we can just switch to the strain. So here's your strain from all kinds of measurement points across the structure. So you can really understand holistically what's going on with your structures and the materials themselves. We can then apply the same capability to entire vehicles or components of vehicles. And in this case, we see the CAD brought in and the strain at the base of a turbine blade. And this turbine blade was patterned with a ceramic pattern and put in a jet engine for 10,000 hours, a year of operation. And this is the creep strain from the blade. Truly impossible measurement, but this was done and is now done on each new design. It invalidated one of their computer models and validated another one. And so this is, now their products are just hugely more accurate than they used to be. We can apply the same technology to looking at any kind of structure, internal or external of a vehicle. We've shown that ARAMIS is able to detect what is called barely visible damage. And so in this case, a slight impact. This was an invisible pattern in the aircraft structure. So we call it smart paint. And so it ends up looking like regular paint, but it actually has the power of millions of strain gauges. And then with thermography, we can look at the extent of impact damage caused by strikes or whatever else, and understand into the structure how the effect of the defect is. And so applying this to complex structures, it becomes as easy as enhanced visual inspection, or just visual inspection, but it's enhanced visual inspection, but it has the power of trillions of strain gauges on your fleet. So the idea of this non-contact capability and full field just is this tremendous power for understanding composites. It really is this engineer's toolbox for dealing with advanced composites. And so we can use this on just a broad range of materials and structures, from small material components to entire vehicles, and be it static loading or dynamic loading, and adjusting it for your validation, and coupling all of this. Our digital twin provides deep memory and understanding of your structures and components over time and across product lines. And again, the savings is pretty substantial in each case. Typically, about 30 days is return on investment of when this equipment's really being used. That's just really powerful. Thank you very much, and I look forward to supporting you across North America and our GOEM team around the world. And if you have any questions, I look forward to answering them.
Thank you so much, John. That was a great presentation. We do have questions, and we're going to start answering those. In the meantime, if we do not get to all the questions while we're on the air, this webinar is being recorded and it will be available online. One of the first questions.
Reach out to me. Please reach out if you need to, otherwise too.
Yep, absolutely. Is there any sample shape or size limit when the camera is applied?
Well, when we're dealing with fields of view, we have so many pixels in our cameras. We have a broad range of different cameras, different detection speeds that they run at too. But again, the accuracy that we're trying to measure is proportional to the field of view of the camera. So we're typically say we're about 20 microns per meter of field of view for the finest resolution. So 20 microns of out-of-plane displacement per meter of field of view. So if we're looking at a smaller field of view, like a 100-millimeter field of view, we're 10 times better than that. And we're always 3 times better than that in plane than the out-of-plane displacement. So that gives you a sense. So for a 100-meter field of view has less local resolution than, say, 10-millimeter field of view.
We have 2 questions about the speckled paint application. One, is it always required for testing and measurement, and how is it applied?
So patterning is just you know a broad topic on its own right, but we can use almost any material for patterning as long as we can resolve it, and and many times we can do it without any patterning at all. But the problem with not patterning is that it's every material is fairly reflective in general, and so we use a flat matte paints typically, and or adjustment illumination can correct for any glare. Glare is a problem because one camera sees it differently than the other, and we need to be able to have a similar image from both. So from the patterning perspective, we can use just a broad range of materials. Most all work is done with a can of spray paint from Home Depot, and this is really simple to apply. But for larger structures, we use vinyl cut out materials, make it super fast. I did the testing on the Merlin engines, 10 foot high, 8 foot in diameter. Took 2 hours to pattern the entire rocket motor.
Can you give an idea of the cost for a simple test system?
So the test systems, start out free and work their way up to a typical system that's used in engineering is about $100,000. That's they're pretty much, plus or minus 50,000 from that is normal test setup.
Okay. Are there available standards or accepted best practices for the selection of facet size and point distance values? How sensitive are the results, for example, measuring modulus to these parameters?
Yeah, so typically we want to be able to measure, most people want to measure compared to a traditional gauging method or a standard. And so we have a simple guide, literally a one-page guide that shows you the comparison of a measurement relative to any field, the cameras that you're using versus that field of view, versus tells you what patterning to do and what its resolution is from a displacement and strain perspective.
Have you applied these kind of systems during maintenance work on aircraft?
Yes, it's very powerful for doing that, and could be extremely powerful if it was fully implemented in a good way. But the ability to be able to look at, say, what visual inspection normally is looking for cracks and things, ARAMIS is 10 times or 100 times more sensitive than a human eye to finding cracks in structures, as well as for looking at dents. We can scan for a dent very, very simply. Even with or without a pattern. We do have scanners for that kind of thing. But patterns typically required for strain measurement.
So you mentioned issues with shiny materials. What about semi-transparent materials?
So semi-transparent materials, again, if we put a pattern on the surface or the backside of it, being able to look through the material and understand it works. We also have other methods that work on transparent materials that utilize polarization parameters.
So I'm not quite sure this next question is talking about how could you use this system in, it's random placement of composite fiber during manufacturing, but I would assume that would have evolved all the way over to oriented placement of fiber during manufacturing.
So when it gets really interesting when we're dealing with COPVs, carbon overwrapped pressure vessels, where the vector of fiber placement changes across the spherical dome. And this is the kind of thing that ARAMIS is just so powerful for, being able to understand the complexities of composite assembly and build, and be able to understand the response of that. In fiber layup, and looking at the fiber alignment, that's a complex scenario, and I can address that individually as desired.
Well, we have reached the top of the hour, and I want to thank Again, John Tyson and Trilion Quality Systems for this webinar. Please do reach out to John and Trilion to learn more. Thank you also to all of our attendees. We very much appreciate your participation, and we hope to see you again soon at the next Composites World webinar. Have a great day, everybody.